All righty. So we are going to continue now. I guess this is what, day 2 of our, or a full second day now of our discussion of the optimal growth model. I think this is where we stopped last time. So we solved analytically for the policy function and the value function for the canonical growth model, the one that has these certain restrictions on utility and production. Today I want to step back a little bit and look at this kind of baseline growth model that doesn't impose so many tight restrictions on preferences and technologies, to see what kind of properties we can derive from this model. So here is the statement then of the basic optimal growth model as a sequence problem that the benevolent central planner would face to maximize over sequences of capital and consumption this lifetime objective function, subject to a period by period resource constraint where the capital stock you take into the next period is equal to whatever you produce today, plus whatever capital is left over after depreciation, minus whatever you decide to consume. Capital has to be non-negative, and the planner is given some initial stock of capital. So this is the statement of the sequence problem. Now, the production function is neoclassical, right? It's going to be increasing, continuous, differentiable, and strictly concave. It's the aggregate production function that it derives from is linearly homogeneous, all that good stuff. It satisfies the Anata conditions. All those nice neoclassical properties of the production function that we talked about in the context of the Solow model carry over here. I do want to take a few minutes to comment on an assumption about the utility function. I think this is assumption 6 in your notes. So we're going to assume here for this model that the instantaneous payoff function is continuous and differentiable on its domain, where the domain is not just the positive reals, but it's slightly restricted in the sense that utility is defined from some lower bound on consumption, which I'm going to call epsilon. You could think of it as just an epsilon greater than 0 all the way to infinity, where utility is going to be increasing and also concave in the interior of that domain. Okay, so what this assumption means then is that consumption every period is going to be greater than or equal to some small epsilon bigger than 0. Now, I don't want you guys to get freaked out by this assumption. It turns out to be stronger than what is needed, but I'm going to make this assumption in order to make the proof of the stability of the steady state in this model a little bit easier to do in the next class, okay? But for all practical purposes, you know, you can think of this as being continuous and differentiable on the domain of consumption, which is essentially approaches 0 asymptotically all the way to infinity, right? Like, for example, log utility would not technically be defined on 0 consumption, right? That would be undefined. It would be all positive values of consumption. Okay. Everybody's cool with that? Okay, so the first step in our process here is to transform the sequence problem into a functional equation. All right, you guys tell me, what does that Bellman equation look like in the optimal growth model? Infinite horizon sequence problem transformed into basically a 2-period functional equation in the unknown value function, right? So the value of pursuing an optimal policy over time is given by V, right? Where the state variable is the current stock of capital, or KT. That's equal to the max of what? The current return, right? Utility depends on consumption. Well, what's consumption equal to? Go up to the resource constraint and solve that for C, and you get f of k plus 1 minus delta k minus k prime. That's the current return. Utility is a function of consumption, where I've substituted the control consumption out of the problem and written it in terms of the new control, that is tomorrow's capital stock, plus the discounted value of the continuation return, V of k prime. The control, k prime, or the policy function that we're looking for, has to live on some constraint correspondence G. What is G defined as? It is a closed and bounded interval on the real line. Its lower bound is 0, and what is the upper bound? What's the highest value that the planner can select for k prime, given what k is today? Well, if the planner chooses to feed this agent nothing, consumption is 0, what is kt plus 1 or k prime going to be equal to? F of k plus 1 minus delta k. K is the state, k prime is the control. You guys have to be able to do this step. This is essential. You have to be able to take a sequence problem and turn it into a functional equation, the correct one. That means writing the Bellman equation properly, identifying what's the state and what's the control, identifying what variable appears in the utility function, and identifying the constraint correspondence correctly. If you cannot get this step, you're dead on arrival, okay? So you got to practice, and it looks slightly different from problem to problem, but you need to be able to go from here to here. The planner is confronted with this problem. This problem is garbage. I don't want to solve this problem. It's too hard to do. I'm lazy. I'm going to solve this problem. It's easier to deal with. All right. Solving what amounts to a 2-period functional equation is easier than solving for an infinite number of controls. Okay. Now, the way we solve these problems is just like we did in the last class. We want to write the first order condition, the envelope condition, combine the two to derive an intertemporal Euler equation. And that equation, in concert with the transversality condition, then fully characterize the solution to this planning problem and also the solution to the sequence problem, because the two problems are equivalent by virtue of all of those theorems that we studied, right? Okay, what I want to do, I'm not going to go through assumption by assumption here for the optimal growth model. In order to apply the theorems that establish the equivalency between these two problems. I'm not going to do that to that extent, but there are a couple of assumptions that I want to verify because I think there's some value added compared to what we did in the last class, okay? Now, what is the key assumption that needs to be satisfied in order for all of those theorems, particularly theorems 1 and 2, to follow from our dynamic programming discussion? In order to prove or establish the existence and uniqueness of the Bellman equation and it being continuous, it must be the case that the relevant state variable, the capital stock, has to live on a closed and bounded set on the real line. The real line is not a compact set. In order to apply the dynamic programming theorems, we have to be certain that the state variable lies on a compact set. Okay, so how did we do that in the last class? How did we prove that K is going to be somewhere on some closed and bounded interval? Let's call it 0 to K hat, which is a closed and bounded subset of the positive reals. How did we prove that? Well, we want to appeal to this piece of information, the aggregate resource constraint that constrains the choice of the planner. Okay, let's think about this. We know that KT has to be bigger than or equal to 0 for all t. That's a physical constraint on the problem. So we know that K is never going to be less than 0. But is it bounded above by some finite number, let's say K hat? It is. How do we prove that? Well, let's assume, for the sake of argument, that consumption is 0 forever. Follow me on this, okay? If consumption is 0 forever, then what does that imply about KT plus 1? That it's equal to f of KT plus 1 minus delta KT for all t. I've just substituted CT is equal to 0 into the resource constraint. What does this look like to you? This looks like a mapping from KT to KT plus 1. It's not the optimal way to choose KT plus 1, right? Certainly a planner is not going to choose CT is equal to 0 forever, but this will imply a mapping from KT to KT plus 1 that probably has a long-run fixed point solution to it, right? What does that mapping look like? Let's draw it. Let's put KT plus 1 on the vertical axis and KT on the horizontal axis. What does the mapping by this equation look like? Well, for K really close to 0, KT plus 1 is going to be 0, right? But what happens to KT plus 1 as KT gets slightly bigger than 0? It increases a lot because of the Inada condition on the production function. F prime is infinite for K small. So it looks kind of like this early on. But what happens over time as KT gets bigger? The slope of F goes to 0, but the slope of the second component goes to 1 minus delta, right? So for a while, the slope of this mapping from KT to KT plus 1 is bigger than 1 minus delta, but eventually it's going to get to a point where the slope is exactly equal to 1 minus delta. Think about that. As K gets really big, what happens to the slope of this mapping? F prime plus 1 minus delta. Well, F prime goes to 0 as K gets really big. Okay? Now, is there going to be a fixed point that K will settle on in the long run? Yeah. You can find that by looking at the point where the 45-degree line intersects this mapping. And how do we know that the 45-degree line will even intersect it? Because in the long run, the slope is 1 minus delta. Delta is positive, so the slope is less than 1. What's the slope of the 45-degree line? 1. So they have to intersect at exactly 1 point. I'm going to call this point K bar. This is the maximum sustainable level of capital in this model. If the planner were to choose consumption equal to 0 forever, eventually the capital stock will settle down to this point, K bar, which is the fixed point of this mapping. In other words, K bar can be characterized as K bar is equal to F of K bar plus 1 minus delta k bar. Cancel, cancel, and f of k bar is equal to delta k bar. That should make intuitive sense. The maximum sustainable level of capital in the long run is such that the capital stock gets so high, diminishing returns set into the point where every bit of output we're producing is just offsetting depreciating capital. And consumption is zero. That's this point way out here. Everybody follow? Now again, this is not the optimal steady state level of capital. This is just the level of capital that is the highest possible, that is sustainable in the long run if people choose zero consumption forever. What this means then is that if initial capital is less than k bar, kt should be less than or equal to k bar for all t. If initial capital is somewhere less than k bar, it's never going to be the case that the capital stock is going to rise above k bar. It's bounded above by k bar. What if initial capital happens to be greater than k bar though? Then that means kt will be less than or equal to initial capital, which is assumed to be finite for all t. If k0 is over here, then the capital stock will decline to this maximum sustainable level in the long run. Let me define k hat as the max of k bar and k0. What we've shown here is that kt must be somewhere between 0 and k hat for all t. So even though we haven't restricted the capital stock to lying on this compact set of the reals, given the technology that is in the problem, we can, without loss of generality, restrict the state variable to lying on this compact set. That way we can actually apply our dynamic programming theorems in order to have the equivalency between the sequence problem and the Bellman equation. And in order for there to be a unique policy function that solves the Bellman equation, it must be the case that the state variable lies on this compact set. We can actually determine what that compact set is given the parameters of the model. Does that make sense? Now, why that one is so important is because if the capital stock lies on a compact set, then it's going to follow from that the utility function is going to be bounded. And if the utility function is bounded, then the planner's lifetime objective function that she's trying to maximize will exist. And so the equivalence of values theorem applies, the principle of optimality applies, etc. Right? Remember what the domain of the Bellman equation problem looks like. It's all k prime pairs that are in the space 0 k hat times 0 to k hat, such that k prime is feasible. Because G is compact valued and continuous, and because the state variable K lives on a compact set, the set of possible K primes is also going to reside on a compact set. Because the utility function is continuous then, Remember, the utility function maps elements of x, g into the reals. The utility function is continuous. That means that u is going to be bounded. Now, why is that helpful? Let's think about this. What's the utility function again? It's u of f of kt plus 1 minus delta kt minus kt plus 1. We know that kt cannot be less than 0. And we know that utility is strictly increasing in consumption. So this utility function here has to be bounded above by the following. U of f of kt plus 1 minus delta kt. Correct? F is strictly increasing in k. 1 minus delta times k is strictly increasing in k. So this has to be bounded above by u of f k hat plus 1 minus delta k hat. And if k hat is finite, and u is a continuous function, then this is going to be finite. This implies then that v of k or I should say v star of k0, let's say. So the value function that solves the sequence problem is going to be equal to the sum from 0 to infinity, beta to the t, u of f kt star plus 1 minus delta kt star minus kt plus 1 star. The stars on k indicate an optimal sequence. We know that that has to be less than 1 over 1 minus beta u fk hat plus 1 minus delta k hat. And that's finite. So the objective function has to exist for any feasible sequence of capital stocks. That's what I'm trying to say there. Okay, imagine the planner has all these different sequences of capital that she is choosing from. It doesn't matter which sequence of capital stocks she selects from time 0 out to time infinity. It is going to result in a value of the lifetime objective function that is finite. Therefore, the Bellman equation and the sequence problem are equivalent. Solutions to one correspond to solutions to the other. Okay? Y'all have any questions so far? Now look, assumption 3 was proving that the utility function is concave in k prime, and that the constraint correspondence is convex. I'm not going to go through that again. I would encourage you to try to demonstrate those two, but just using general utility and production function arguments rather than the specific ones. But the proof is exactly the same. So the utility function is concave. The constraint correspondence is convex. It follows then that what? The value function is strictly concave. And when the value function is concave, we know that a unique optimal policy function will satisfy the Bellman equation, that there's only one optimal sequence of K's and C's in this model. Okay? We also established a few assumptions that would give us some useful properties on the value function. One is that the value function is strictly increasing in the state K, and the other is that it's continuously differentiable. The utility function we're going to use is differentiable. So that last assumption follows naturally from that. Okay. What was required in order to establish that the value function is strictly increasing? In other words, how do we know this? How do we know that increasing the capital stock is going to result in a higher value function for any k? This follows from the utility function being strictly increasing in the state, as well as the constraint set being monotonic. Okay? Now, what is the partial of u with respect to k? Is the utility function increasing in the capital stock? Well, let's go through the derivatives. It's u prime of c, right, times the derivative of c with respect to k, which is f prime of k plus 1 minus delta. Is u prime of c positive or negative? Utility is increasing in consumption. What's the sign of this? What's f prime of k? Is that positive or negative? It's positive. Plus 1 minus delta is positive. So it's a positive times a positive is a positive. So you increase the capital stock, you're going to increase the value of utility. Now, remember that the constraint set is defined as 0 to f of k plus 1 minus delta k. Is the constraint set monotonic, or is it a monotone constraint set? How can we easily demonstrate that? What does it mean for G to be monotone? Let's start with that. You got to know what we're talking about here. If G is a monotone constraint set, what does that mean? It's not a function, so it's not increasing in the sense of an increasing function. What does a monotone set mean?
Like increase your set of possible values and increase capital.
Yeah, making k bigger basically widens the bounds here. Well, then you're never going to get less than 0, right? So if G is monotone, then it must be the upper bound that gets bigger. Well, that's easy to show, right? The upper bound is just given by f of k plus 1 minus delta k. Well, what's the derivative of that? It's f prime of k plus 1 minus delta, which is positive. So increasing the capital stock is going to push the upper bound of G farther to the right on the real line. So in fact, G is monotone. Okay? Y'all have any questions about that? We are ready to do proposition 1. Let me restate the Bellman equation first here, just to be formal about this. All right, here is the recursive statement of the optimal growth problem, okay? We've already been over this. This must be true for any possible value of k on its feasible set 0 to k hat. What does proposition 1 say? Okay, so I'm just going to read it and then we'll go over the proof of it. Given assumptions 1, 2, all that stuff we talked about in the last section of the course on dynamic programming, and also given this assumption about the utility function that I stated at the top of class today, the optimal growth model has 1, a solution characterized by a unique value function, v, and a consumption function, let's call it c of k, and a capital stock in the next period, k prime, given by k prime is equal to s of k. So I called that in the last class pi of k, but let me just keep the notation. I think I call it in your notes s of k. Moreover, the value function v is strictly increasing, strictly concave, and the policy function for the capital stock s of k is non-decreasing in k. How many of those things have we already established? All but one, right? We know that our dynamic programming theorems tell us that the value function is unique and that the policy functions for capital and consumption are also unique. The dynamic programming theorems also tell us that the value function is strictly increasing and strictly concave. So simply verifying those assumptions that we've already done now twice are enough to get all of that. The only thing we technically haven't shown in proposition 1 is this idea that s of k, so the optimal value of k prime, is going to be given by some time invariant policy function s of k, where s is non-decreasing. So how do we interpret that? That means if you suddenly increase your endowment of capital this period, if s is non-decreasing, then that means your choice for k prime is not going to be lower than it otherwise would have been. That raising the capital stock today essentially implies that your choice of capital for tomorrow is also going to be higher. Okay, now you actually can thank Buddy, who was a student in this class last year, for giving a suggestion on how we can simplify this proof. So the way I'd always done this is by actually appealing to some more primitive arguments to establish that s is non-decreasing, where I do a kind of a long, complicated proof by contradiction. Okay, I assume that s is actually increasing, and then I go through the steps and show that that leads to a direct contradiction on the concavity of the utility function. That is certainly one way to go. And if you're interested in seeing that proof, I'm more than happy to let you guys look at it after class or take a picture or make a copy or whatever. But Buddy actually showed me there's a much easier way to do this, as long as you're willing to assume that the utility function and the value function are differentiable, right? So the proof that I've always done doesn't rely on a differentiability argument. But since we're always dealing with differentiable functions in this class, I'm going to do the easier one, okay? We want to prove that s of k is non-decreasing. Okay, well, how do we do that? I think the easiest place to start is to actually write the first order condition for this problem, right? So what would it look like? Well, it would be what? U prime of f of k plus 1 minus delta k minus k prime times the -1. Right, you guys got to be able to do these first order conditions. So what's the derivative of the value function with respect to k prime? So it would be u prime and then there's a chain rule argument here times -1 plus beta times V. I've got a mistake here, which you guys did not see. Shame on you. This is V of K prime, not V prime of K. So it would be beta V prime of K prime. This should be equal to 0 at the optimal value for K prime, correct? Okay, well, let's simplify this a little bit. So this is U prime of C, and this would just be the optimal value of consumption, would be equal to beta times V prime of, let's see, K prime star is S of K, right? That's the time invariant policy function for K. Let me write this out longhand just so no one is confused by this. Hold on one sec. So instead of substituting in consumption right now, let me write this as F of K plus 1 minus delta K minus K prime star is S of K is equal to beta V prime S of K. Okay, that's the first order condition. Now what Buddy suggested, and I don't know why I didn't see this earlier, is if U and V are twice continuously differentiable, then why not just take the derivative of the first order condition with respect to K itself? I don't see why we can't do that, right? S is assumed to be a continuous function of K. U and V are continuous functions of K. So why not just take the derivative then with respect to K directly? And what happens? Well, this is U double prime of, this is C, right? Times, what's the derivative of this with respect to K? It would be F prime of K plus 1 minus delta minus S prime of K is equal to beta V double prime S of K times S prime of K. You guys follow that? So this isn't a second order condition. This is a derivative of the first order condition with respect to the state. Kind of like an envelope condition on the first order condition directly. Well, notice here that we should be able to group terms on the S prime of K variable, right? This would be U double prime of C times F prime of K plus 1 minus delta is equal to U double prime of C plus beta V double prime of S of K times S prime of K. So S prime of K is U double prime of C, F prime of K plus 1 minus delta divided by U double prime of C plus beta V double prime S of K. Now, all we need to show is that S is non-decreasing. Is there enough there to demonstrate that? Well, what is the sign of U double prime? Is it positive or negative?
Negative.
It's negative. Utility function is strictly concave. What's the sign of f prime plus 1 minus delta?
Positive.
Positive. So the numerator is a negative number. What about the denominator? U double prime is negative plus beta V double prime. What's the sign of V double prime?
Also negative.
It's also negative. Why? Because we know that the value function is strictly concave. So this looks like a negative over a negative, making it a positive. I think that's a better proof. It's a more elegant, well, I don't want to say it. It's more elegant in that it's not as many lines. And it does require that we assume differentiability and continuous differentiability. The proof that I have doesn't rely on, it's based on more primitive arguments. But essentially what you do is you assume that S is increasing, and then you take two different values of K, let's say a K and a K tilde, where K tilde is assumed to be bigger than K, and you set up the two value functions, and then you can actually determine that from the first order conditions of those problems, or I'm sorry, from the Bellman equations of those problems, that you're going to violate the strict concavity of the utility function if you have S being an increasing function. It's just it's a somewhat more involved proof. This one relies on taking derivatives and is a little cleaner in that sense. Now, again, you may be thinking, well, why is this so important? We need to establish that the policy function for K prime is strictly increasing in the capital stock in order for us to establish the stability of the steady state in this model. This whole idea of monotonic convergence to a steady state is going to also rely on this being satisfied, that the policy function itself has to be non-decreasing. So we didn't just do this for fun. It's going to help us actually prove a proposition in the next class. Okay. If there are no questions about that, let me move on to the next task at hand. So what I would like to do is characterize the full equilibrium of this model. So we've set up the planner's Bellman equation, okay? And we've characterized the solution to that Bellman equation. And we've derived some useful properties about the policy function, all right? But now what I'd like to do is derive a full statement of the equilibrium of this model, all right? So how do we do that? Well, what you want to do is you want to start with the Bellman equation and derive the key equilibrium conditions of this model, okay? The first one, of course, is going to be derived from the first order condition of the problem, which we've already done now a few times. So negative U prime f of k plus 1 minus delta k minus k prime star plus beta v prime k prime star is equal to 0. Now, how do we solve or characterize the solution or the policy function to the planner's problem? we need to eliminate the value function argument from this first order condition. How do we do that? We appeal to the envelope condition, which in this problem is u prime of c, basically, times f prime of k plus 1 minus delta. All right, then what we want to do is we want to take the envelope condition and plug it back into the first order condition so that we can write this whole thing, so we can derive the intertemporal Euler equations that are absent these value function arguments. So how do we do that? We have to scroll forward the envelope condition one period and plug it in up here, right? The envelope condition is a v prime of k, and what the first order condition has is a v prime of k prime. All right, so we've got to scroll this thing forward one period and then substitute it in above. Now, as I do this, I'm going to reinsert, now be careful about this, I'm going to reinsert the time subscripts into the equations, because what I'd like to do is write the list of equilibrium conditions for this model. Okay, so for instance, the first order condition here can be written as u prime of ct is equal to beta v prime of k t plus 1, right? And the envelope condition can be written as v prime of kt is equal to u prime of ct times f prime of kt plus 1 minus delta. So what I want to do is update the envelope condition one period and shove it into the first order condition. And what do I get? I get a u prime of ct is equal to beta times, let's see, u prime of ct plus 1 times f prime of kt plus 1 plus 1 minus delta. That is the intertemporal Euler equation. That's key equation number 1. What is the second key equation of this equilibrium? So we've got the intertemporal Euler equation, but we need the transversality condition to hold along an optimal path as well. That's the limit as t goes to infinity of beta to the t times the marginal value of the state times the state. So u prime of ct times f prime of kt plus 1 minus delta times kt is equal to 0. And then the third equation that characterizes the equilibrium of the model would just be the resource constraint. Ct plus kt plus 1 is equal to f of kt plus 1 minus delta kt. Okay, so what is an equilibrium in this model? It is a sequence of c's and k's that satisfy these equations for some given stock of initial capital. Now be careful here. I've always told you that the number of equations you need is equal to the number of unknown variables in your sequence. Well, notice I've got 3 equations here with just 2 of these guys. Well, that's true because in an infinite horizon maximization problem, you need a terminal value condition as well. So you need the intertemporal Euler equation, you need the period by period resource constraint, and you also need the transversality condition. For some given initial capital stock, this is a full statement then of the stationary equilibrium of the planner's problem. It's not a competitive equilibrium because it's a central planner problem. There are no markets here. Allocations are just being distributed by a central planner. You guys see how I did that? Let me make just one more remark about this Euler equation so that you can contrast it with what we've done in the past. Hopefully you guys notice here that the key equilibrium condition in this model, which is this intertemporal Euler equation, implies a type of equation between kt and kt plus 1, right? We can notice that we can rewrite this as u prime. What is ct? Ct is f of kt plus 1 minus delta kt minus kt plus 1 is equal to beta times u prime of ct plus 1. Well, that's f of kt plus 1 plus 1 minus delta kt plus 1 minus kt plus 2 times f prime of kt plus 1 plus 1 minus delta. So here I'm combining equations 3 and 1. And what does that give me? This is a difference equation just in the capital stock, right? But notice here you've got KTs, you've got KT plus 1s, but you've also got a KT plus 2. So unlike the solo growth model, unlike the OLG model, this is a second order difference equation that doesn't just express KT plus 1 as an implicit function of KT, but rather it has KT plus 2 and KT plus 1, depending on KT. Now, fortunately, dynamic programming can be used to derive the policy function, which shows us how KT plus 1 is a function of KT and solves this second order difference equation. That's the beauty of dynamic programming there, is that we can solve that second order difference equation using the techniques that I showed you from the last class. But this is, I wanted to write it this way to show you how this is kind of related to or contrasts with what we've done so far, right? We wrote the solo model, and the key object that we tried to find was this law of motion for the capital stock, which shows how KT plus 1 depends on KT. In the OLG model, we solved for a young agent's savings decision, and from that derived the law of motion for capital, which shows how KT plus 1 depends on KT, at least implicitly, right? In the dynamic programming optimal growth model, we can derive an equation that shows how KT plus 1 and KT plus 2 depend on KT. It's a second order difference equation, not a first order difference equation. We can derive the optimal mapping implied by that equation using our dynamic programming theorems, along with these guess and verify strategies we talked about in the last class. Of course, in more complicated problems, you'll need to enlist the help of a computer in order to approximate what the policy function looks like. But it all is based on the same analytical framework. All right, we've characterized the equilibrium of the model. Now we want to look at the steady state. Does it exist? Is it unique? Okay, how do we find the steady state? The steady state is a point at which the capital stock converges to some fixed point, K star, and consumption converges to some fixed point C star. How do we characterize K star and C star? What are the equations that must be satisfied by the steady state if it exists? Well, what are the two key equations in your statement of an equilibrium? One is the Euler equation, right? U prime of CT is equal to beta U prime of CT plus 1 times F prime of KT plus 1 minus delta. That Euler equation must be satisfied for all t, including in the steady state. So U prime of C star must be equal to beta U prime of C star, F prime of K star plus 1 minus delta. U prime is strictly positive, so you can divide both sides by the marginal utility of consumption. And what are you left with? F prime of K star should be equal to beta inverse minus 1 plus delta. So if a steady state value of capital exists, it must satisfy that equation. How do we characterize this steady state for consumption then? What's the other key equation of the model is the resource constraint, which says that KT plus 1 plus CT is equal to F of KT plus 1 minus delta KT. That resource constraint has to hold forever, including the steady state. So K star plus C star is equal to F of K star plus 1 minus delta K star. Cancel, cancel. C star is equal to F of K star minus delta K star. So if a capital stock in the steady state exists and is unique, then the steady state level of consumption exists and is unique. These two equations here characterize the steady state of the optimal growth model. If we know what the production function is, we can actually solve them explicitly. You'll notice that the steady state does not depend on the utility function. It does not matter the explicit way in which you rank consumption bundles. The only things that matter for the steady state are the production technology, the depreciation rate, and the time rate of preference. But any parameters or any way that you want to rank consumption bundles in your utility function don't actually matter. The utility function does not show up. That result does not generalize, by the way, to the inclusion of labor augmenting technology. I think you may see a review question that looks at technological growth, and it won't quite generalize to that. Okay? Can we prove the existence and uniqueness of the steady state? Yes. In fact, it's easier to do than even in the solo model, right? Look at the steady state equation for the capital stock. F prime is equal to some constant, right?
Wait, isn't that prop 2?
Prop 2, you're right. I've lost count. Existence. The limit as k goes to 0 of f prime of k is equal to infinity. The limit as k goes to infinity of f prime of k is equal to 0. That's the Anata conditions that we've assumed. F prime of k is continuous, so there exists some k star between 0 and infinity, such that f prime of k star has to be equal to beta inverse minus 1 plus delta. Which is bigger than 0 and less than infinity. So it's the exact same proof that we saw in the Solow model. It relies on the anotic conditions and the continuity of the production function. That's what, the intermediate value theorem, right? What about uniqueness? How do we prove that this steady state is the only one that exists? F double prime of k is less than 0 for all k. F is strictly concave by assumption, right? Therefore, this f prime is strictly decreasing in k, so it can only intersect beta inverse minus 1 plus delta in exactly one spot. You guys remember seeing this, don't you? Here's my different possible values for k. I'm going to graph f prime of k. It looks like this because of the anotic conditions and because f is strictly concave. The intersection gives me k star. Yep. One last thing, just to make this complete. Are we sure the transversality condition is satisfied? What's the transversality condition again? Limit as t goes to infinity of beta to the t, u prime of ct, f prime of kt plus 1 minus delta times kt. That better be equal to 0 in order for the transversality condition to be satisfied. Well, what have we just demonstrated? That as t goes to infinity, where does consumption and capital go to? They go to the steady state, right? So this could be written as the limit as t goes to infinity of beta to the t u prime of c star times f prime of k star plus 1 minus delta times k star. What's f prime of k star plus 1 minus delta equal to? You can rearrange the steady state condition for capital and show that that is equal to beta inverse. So this becomes 1 over beta u prime of c star times k star times the limit as t goes to infinity of beta to the t. What's that limit expression equal? 0, because beta is a fraction. So the transversality condition is indeed satisfied. Let's do some comparative statics. But I'm not going to do any math. I'm just going to draw pictures. I'll let you do the math. Okay, this is the picture I just drew on the last page, right? This is the steady state condition. It's the point at which f prime of k is exactly equal to beta inverse minus 1 plus delta. We know that there exists a unique steady state value of capital that lies at that intersection point. Let's do some comparative statics. What if I ask you to compute how does steady state capital change if there is a marginal increase in the discount factor? Well, first of all, how would you do this mathematically? You would go back to this equation and take the derivative of both sides with respect to beta, right? And then you could actually get an explicit solution for dk d beta. I'm assuming you know how to take derivatives. Let's draw a picture. What does your intuition tell you should be the sign of this derivative? What's going to happen if there's a marginal increase in beta?
In case they start decreases.
This is beta inverse minus 1 plus delta, right?
Okay, so sorry.
So if beta goes up, 1 over beta gets smaller. So this whole line here shifts down, and that's going to lead to a increase in steady state capital. Does that make sense? Yeah. Beta going up means that agents are more patient. They're not discounting the future as heavily. When that's the case, individuals are going to want to save more, and therefore the capital stock is going to be higher in the long run. What about dk d delta? What if the depreciation rate goes up? What happens to steady state capital? This horizontal line is going to shift up, right? In which case, the steady state capital stock is going to decline. That makes sense. As machines wear out more quickly, all else equal, that's going to cause the capital stock to decline in the long run. What if I ask you, let's suppose we reinsert this technology parameter A back into the production function. What would happen if there's an improvement in productivity? How would that affect the steady state value of capital, you think?
We should increase K star, right?
It doesn't affect this horizontal line. That's only dependent on beta and delta.
Does it shift out the curve?
F prime, that's the marginal product of capital, right? An improvement in productivity is probably going to raise the marginal product of capital. You can think of it in terms of like a Cobb-Douglas production function, where A is this shift parameter, right? And so that should cause an increase in steady state capital. So anything that shifts the marginal product of capital, or anything that shifts this horizontal line, is going to change the steady state value of the capital stock. You can derive those mathematically by taking derivatives directly on the Euler equation, that steady state condition, or you can do it graphically. I like the picture. It's a little bit more intuitive and kind of helps translate the math. You guys have any questions about that? we've got one more day and we should have plenty of time to finish this topic. And essentially the only thing we need to do in the next class is prove proposition 3, which is that the optimal growth model exhibits a monotonically convergent, globally stable steady state. So regardless if initial capital is really low or high, we should converge to K star in the long run, making the optimal growth model appear to have the same type of dynamic structure in the long run as the solo model. So even though the optimal growth model has optimizing behavior, it's going to look a lot like the solo model in the long run and have monotonic convergence towards a steady state. I will do that proof, and then if we have any time left, I'm going to go back a little bit and show you guys one other way of solving analytically these Bellman equations. So the way we did it in class, if you'll recall, was we set up the Bellman equation, we derived the first order condition, and then we guessed the policy function, right? And then we solved for the undetermined coefficients in the policy function. There is an alternative way to solve those problems where instead of guessing the policy function directly, you can guess the form of the value function directly and work from that. And then and you should get exactly the same results. So if I have time, I'll go back and show you that alternative way of doing it. I don't really care which method you guys use. Some of you may find the policy function guess to be easier. Some of you may find the value function guess to be more straightforward to work with. But time available, we'll go back and do that before we move on to the next topic, which is the neoclassical growth model, which looks at this same basic economic environment, but from the perspective of a decentralized competitive market equilibrium. So not a social planner, but households that are choosing their consumption optimally, subject to budget constraints, and firms that are choosing their inputs optimally to maximize profits. Doing the model that way will introduce us to some new concepts, in particular the phase diagram and this thing called a balanced, the saddle path solution, which is a unique concept to that class of models. Okay, that'll take probably a couple of weeks to get through that, and then we'll have your next exam. So probably not until like early November, my guess. All right.